All right. Yeah, it's going to hear you. Yeah, it's going to hear you. All right. When we left off, we had talked about two different types of polynomials. One that led with an even numbered exponent, which looked like a parabola. Remember that word, parabola? And then ones with a odd number leading exponent, which looked like a snaky thing. That's a technical term, snaky thing. Snaky thing in the math glossary. Look up snaky thing, you'll see one of those. All right? Now we're off to exercise 1, which is page 2 of your packet. Now, consider this function. F of x equals 2x to the 4th plus x cubed minus x squared plus 5x plus 3. Do you think that your curve will look more like this guy or more like this guy? Somebody put some.
Yeah.
Okay.
Oh my God. I think I'm failed.
No, it smells like tea leaf.
I don't like feelings.
Okay. So which one? Is it going to look like the one on the right or the one on the left? Who says left? The right hands.
No.
1, 2, 3, 4, 5, 6. I see 6. So 6 for was that for the right or the left? That was for the left. 6 for the left. Okay. How many do you think the right? The one on the right?
The rest are 5.
1, 2, 3, 4, 5.
People get penalized for not voting.
Okay, so how many you just don't know? How many you just don't care?
I don't know.
Good. Okay. How many people have both arms broken? All right. So, remember, leading exponent here is what? Even or odd? So which one is it going to look like? Is it going to look like the one here that's got the even exponent? Or the one down here that's got the odd exponent leading? I gave you graph paper. Oh, you were with Mr. Erickson yesterday.
Yeah.
All right. Okay. All right. So, this guy's going to look like this guy. It's going to look more like that guy, but not exactly. Okay? Yes, I got a bunch over there. Cora, can you do Brandon a favor and hand him a sheet? All right. Now it says graph the function using the graphing utility to check the prediction. So, here's what we're going to do. We're going to go to my favorite web utility. Brandon? All right. Who wants to read me the function? F of x equals, what's the function again? 2x to the 4th. What's the next term? Plus x cubed minus x squared plus 5x plus 3. Okay. So here is my function. Does it look more like the graph on the left? Does it look more like the graph on the left or the graph on the right? The left. The left. See? It looks more like the graph on the left. Okay. So, wait, wrong. There we go. All right. Now, consider this function. F of x equals 2x to the 5th minus x to the 4th minus 2x cubed plus 4x squared plus x plus 3.
You can't just guess, you gotta do the work.
Well, what do you think it's going to look like? The one on the left, this guy, or the one on the right, this guy? Who thinks left? Show of hands, left.
Right.
So we got 1, 2, 3, 4, 5, 6 again. Who thinks the one on the right? 1, 2, I see more people. So 2, 4, 6, 7, 8 on the right. Okay, let's graph this guy real quick. Can you read me that one, Taylor? 2x to the 5th, x to the 4th. Yep.
Somebody go die.
4x squared.
Wait, yeah.
Now,
Do it.
look at our graph. Listen up. Look at the graph. Does it look more like the one on the left or the one on the right? Yeah, it looks more like the one on the right. But there are some differences, aren't there? It's got a dip in there, don't it? How high do you think it goes on the right? Goes forever, right? How low do you think it goes on the left? Let's go back to that x to the 4th one. How high do you think it goes on the right? And it goes high on the left too, doesn't it? Goes forever. And there's a very good reason for that we'll get to in the near future. All right. So, thinking back to our discussion of x-intercepts on graphs of polynomial functions, sketch a graph of even degree polynomial function that has no x-intercepts. What does that mean? Right. What is an even-powered polynomial? Thinking back to our discussion, sketch a graph of an even degree polynomial. What does our even degree polynomials look like? Do they look like a U or do they look like the snaky thing? U. They look like the U, right? So, I need to draw something that looks like a U. Now, what does it mean to draw something that has no x-intercepts? What does it look like to have no x-intercepts? Should it be like this? How many x-intercepts does that have? 2. That's not what they're looking for. How about this? Does that have an x-intercept? How many does it have, Smith? It's got 1. Now, if I take that thing and I just move it up a touch, now it doesn't have any x-intercepts. Winner, winner, chicken dinner, right? Could I do this? Is that? How about the green one? Is that a even degree polynomial? It's upside down, but it's a U shape, right? It's just an upside down U. You could do that too. Now, I ask you, can you sketch a odd degree polynomial with no x-intercepts? What do you think, Zach? Yeah. Not possible? Not possible. Go for it. Yeah. So it looks like a snaky thing, right? Yeah, just do that. And it either does this or it does this, right? But what's in the middle all the time? So it either goes like that, or it could go like that. but either one is going to cross the x-axis at least once, right? You're right. I'll just draw one of them. Okay. So, some features. Those polynomials with odd degree. Those polynomials with odd degree have to cross the x-axis at least one time. Now, if we go back to that graph that we did of my odd degree polynomial, that thing, let's see, that thing has a hump. What if this was moved down a few units? How many times could this cross the x-axis? Could cross 3, right? Let's do this. Backspace, backspace. That crosses twice, right? Oh no, 3 times. 1, 2, and it's hard to see the third one. 2 and 3. You see that? So it could cross as many as 3 times. It could cross twice, but it has to cross once. Okay? All right. Exercise 2. The Center for Transportation Analysis studies all transportation in the United States, from energy and environmental concerns to safety and security challenges. A 1997 study compiled the following data of fuel economy and miles per gallon of a car or light truck at various speeds measured in miles per hour. The data accompanied are below. Ooh. So what's this saying to me? Ooh, this is interesting. Here's what we're going to do. We're going to plot this data using a graphing utility. Are we going to plot this using a graphing utility? All right, let's do that. Let's do that. On my left, I have the data. Check this out. We're going to plot some data. We're going to plot some data using my favorite plotting utility, Desmos. Check this out. Add a table. No, not on the test. When speed equals 15, fuel economy equals 24.4. 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, and 75. So now, what are my data for each speed? 27.9, 30.5, 31.7. I want this to... All right. Now, as I put this data in, Bailey, as I put this data in, is that right? Yep. 31.6. Ooh, no. Look on your table on the next page, dude. 31.6, 32.4, 32.4, 31.4, 29.2, and 26.8, and 24.8. Okay, so now I ask you, so we've plotted the data here, right? Everybody look up at the board. Look at the data that we got there. Which quantity is the independent value, the speed or the fuel economy? Speed is my x-axis, right? That is my independent value, which means that my vertical axis is my dependent value. Could you please, Manny? Thank you. Okay? Now, look at question B. It says on question B, this data can be modeled using a polynomial function. Determine if the function that models the data would have an even or odd degree. Now, would you say this looks more like a U or a snaky thing?
Looks like a spider. No, actually,
Now remember,
a bird.
the biggest thing about our snake thing is it went either up in one direction and down the other direction. So this goes down on both sides, right? So would that be an even degree polynomial or an odd degree polynomial? Probably even, because odds do this, right? Evens do either this or this. They're not going to get that on the video today, but that's the reason why I need to be here, so you can see me do weird things with my hands. All right, so even number polynomial, right? The next question asks, is the leading coefficient of the polynomial that we can use to model this data be positive or negative? We haven't gone over this yet, but think about this. Think about this. I want to add something here. I'm going to add a page. I'm going to draw a graph. This that is x squared, yes? Yes. I ask you, what do you think? I'm going to call this g of x. I'm just giving my function a different name. Instead of calling it f, I'm calling it g. What if I ask you what negative x squared looked like? What do you think that would look like?
Just flip it.
Flip it. Flip it like this, Bailey? Flip it like that?
No.
Flip it like that.
Reflect it across the x-axis.
Reflect it? Oh my gosh. That is like perfectly stated. Reflect it across the x-axis. So negative x squared is going to look something like that. So let's go back to my data. This is even exponent or even degree. Is it going to have a positive leading coefficient or a negative leading coefficient? Positives do this, right? Positives look like a touchdown. Negative, I call them smilers. Positive leading coefficient are smilers. Negative leading coefficients are frowners. This guy it's got a little hump in the middle, right? A wall, but it's definitely a frowner. It looks like Charlie Brown after he misses the football. No, I don't think Charlie Brown. Well, his face, his smile, or his frown. Am I actually serious? I am serious. What's up?
Monday.
No, you're taking a test on Monday.
What? You said you want to movie.
Yeah, well, me and Mr. Erickson had a talk and we decided we had to get a test.
Oh, that's unfair.
Okay, so this is letter C. This is going to be a negative leading coefficient. Now, there's two possible reasons the data might have the shape that it does. Why does the data look like that? Very insightful. But think about the why. What am I graphing? Comparing speed of the vehicles to gas mileage, right?
The faster you go.
Think about it. If I drive faster, then what's happening to my car? It's going through what?
Our cans are going up and down.
Okay, how do I put this?
Overdrive.
If I'm driving slow and I stick my hand out the window, what happens to it?
They go back.
It's a little bit, right? Well, I'm driving slow, so it doesn't do much, right? Matter of fact, you can barely feel it. But if I'm driving really fast,
The car is going faster than
what happens to my hand when I stick it out the window when the car is going really fast? It's hard to hold it. It's hard to hold it out here. If I do that, I can do airplane things, right? But what's that telling me? Aerodynamics. There's more wind resistance there, right? There's more air resistance when I go fast. That explains this stuff right here, right? What about this though? I'm getting faster here. I'm getting faster. My wind resistance is going up, but I'm still getting better gas mileage. Why do you think that might be?
what?
Right.
Well, no, I'm sorry, roll down my
Here,
window.
let me ask you this. When I'm designing, listen up guys, when I'm designing a car, do I want it to be most efficient at 10 miles an hour?
No, most of that's 60.
At like highway speed, right? Or close to it.
Overdrive.
So my engineers probably want this plateau, this efficiency spike. Look at that efficiency spike right there at roughly 50 miles an hour. Almost 55. So that might be a design consideration for engineers when they're designing the car. Okay? So, I'm going to give you guys, let's see, where do they go? Where did they go? Well, the lesson's done. So, yay.